All right. Hello, everyone. Here we have our second digital lecture. I'm going to try and figure this out as best I can. It's still new technology to me. So in class, we were talking about spanning sets. I'm going to have two of these, one for span and spanning sets and that kind of stuff. The other we'll talk about linear dependence and independence. So this first one will mostly focus on spanning. So why don't we start with, oh, this is still weird. So we have axes. Oh god, that wasn't anywhere near straight. Good enough. I can make them bigger maybe. There we go. Whoa, axes, awesome. And so what we looked at last time was, let's say we have some vector. So this is what we were looking at in class. If I have a vector here, the span of that vector is everywhere. If I start at the origin, everywhere I can go with this vector, okay? So this creates kind of a line. Maybe, oh, I got colors here. This is fancy. Let's make a yellow line here. Oh, that doesn't show up too well, but whatever. So I can go kind of anywhere on this line that's not straight, using that vector. Starting at the origin, I can kind of go anywhere on this line. So, for example, let's say, excuse me, let's say I wanted to go, here. I can use this vector starting at the origin to get there, right? So here's one of those vectors. Here's second, and then maybe half, okay? So if this is a vector u, I use two full ones, and then maybe like a half of the vector u. So in order to get to this point, it's, 2 and 1/2 u, and I can get to this point, right? So this point is in the span of u, or that's not worded quite correctly. The vector that is the vector all the way out to here is in the span of u. So that vector representation is in the span of u, I should say. So let's look at another example here. Let's say I have some other vector here, v, and let's pick another color. How about green, the best color? Create a line here. This is really hard to do. That's kind of straight. Hey, all right. This green line now represents the span of v. So any vector on this line I can get to, right? So if I want to get, this crazy big vector, I can. I take 1, 2, 3. Oh man, I'm like drunk or something. 4v, right? V. That's supposed to be a v. So 4v gives me that whole vector, and and I can go negative, so I could do like negative 3v to get way down here into this area over here. So this line represents the span of v, everywhere I can get using v, whereas the yellow line here represents the span of u, everywhere I can get with u alone. Okay, so span of one vector is fairly simple. It's everywhere you can go with that vector. Now with two vectors, the span of two vectors, that's certainly different and going to be interesting. So let's make a new page here. Boom. Make some new coordinate axes. Oh, my system's lagging here a bit. Where do you go? Where do you catch up with yourself? Come on. Oh, there we go. Yeah, let me restart this. Bam. Okay. So y, x-axis. All right. And let's go real simple. So let's say I have this vector here along the x-axis and this vector here along the y-axis. Kind of our set standard basic vectors, E1 and E2. Okay. Now I can get to any vector inside of my plane anywhere using some combination of E1 and E2. So let's draw some random vector here. Boom. Right? So how do I get there? Well, I'm going to take a bunch of negative E1s. So there's negative 1 E1, negative 2 E1, negative 3 E1, negative 4 E1, negative 5 E1. That looks about right. And then head down, negative 1 E2, negative 2 E2, negative 3 E2, and negative 4 E2. So, right, so we have 1, 2, 3, 4, 5, negative 5 E1. This darn thing. Work. Negative 5 E1, and this is negative 4 E2 to get to this vector. So, you know, this vector is essentially negative 5, negative 4, and that vector is in the span of E1 and E2. I can create that vector. This is equal to negative 5 E1 plus negative 4 E2, right? Now this is, you know, E1 is a standard, 1, 0, and E2 is your standard 0, 1. Okay, and that's fairly easy to see, right? We have the first component's negative 5, so obviously we need negative 5 E1s, and the second component is negative 4, sorry, so you need negative 4 E2s. Okay, but we can do this with kind of non-standard vectors. So let me create a new page, new set of axes here, and let's make two different vectors here. So there's one vector, and there's another vector, and I'll call this one V maybe, and we'll call that one U. Okay, and let's try and get, you know, here maybe. So whatever the hell that is. Well, I can start with my V's, not a big deal. Where did I start? So there's negative 1V, negative 2V's, negative 3V's, and then maybe like half a V like that, or something like that, half a negative V, and then maybe half of a positive U. So we have here maybe negative 3V, and maybe, oh wait, that was 3.5. Shoot. So maybe, here, I'll cheat a little. Negative 1/2 V minus, see? Negative 3.5 totally works. And this was like 1/2 U. Oh, come on, computer, catch up. There we go. 1/2 U. So this new vector I have is negative 3.5 V's. It's bugging me. Plus 1/2 U. So this vector is in the span of U and V. I can use my vectors U and V to get this vector, that new vector I put in. How about let's do another vector here. Where's my mouse here? Did this thing die already? Shoot. Oh, it's still kind of going. Come on. Oh, there we go. Okay. So, something like that. Negative 1U, negative 2U, negative 3U, and maybe that's 1V. Okay, negative 3U. So this vector as well is in the span. And it turns out with these vectors U and V, everything inside of this plane, so here we're dealing with R2, everything in R2 is in the span of U and V. So we can write that as span UV is equal to all of R2, right? This is span of UV is all of R2 here. Now, I mean, we're looking at these things very geometrically, and in some sense it's kind of easy to look at these things and be able to say, like, okay, well, the span of these vectors is clearly this thing, this space. But, you know, if I were to just give you two random vectors or something like that, so let's say I say U, the vector U is equal to 1, 2, 3, and the vector v is equal to 2, 1, 2, something like that. And I ask you, what is the span of these two vectors? So, I mean, I'm jumping up to three-dimensional space, but yeah, I could ask, what is this? So the span of u and v. I'm asking you, okay, what is that? You know, and this is a very much more algebraic thing. It's a lot more difficult than, you know, if I draw three-dimensional axes here, and I have a vector like that and a vector like that, and looking at the span of them, you know, that's very different than algebraically figuring out what is the span of these two vectors. So first off, we need to determine, are these vectors, so one vector we know, so long as it's not the zero vector, one vector will span a one-dimensional space. Potentially the second vector will add a second dimension to our space, or it'll just continue to add to that first dimension, or not add to that first dimension, but stay in that first dimension. And we need to figure that out. And the way we're going to do this algebraically is we're going to make a matrix with those vectors. Okay, so let's make a little matrix here. Vector u as my first row, vector v as my second row. Okay, so let's write this out, this matrix. Let's see if I can do this. 1, 2, 3, 2, 1, 2. Okay, now with this matrix, what we're going to do is we're going to row reduce this. So I'm just going to kind of do this real fast. R2 minus 2R1, and what do we get here? So the first is 1, 2, 3. We have what here? 0, negative 3, negative 4, something like that. Now, once we've row reduced it, really what we want to know is the rank of this matrix. And we can see here, this is row reduced, or reduced, there's so many terms I don't even know anymore. The rank, then, of this matrix, the rank of UV is equal to 2. And this, 2, this represents the dimension of the space that is the span of these two vectors. Okay, so these two vectors are going to span two-dimensional space in R3. Okay, so what does that mean? That means that the span of these two vectors is a plane in R3. Well, let's figure out, okay, what plane is that? Well, we can use the very simple planar form of, let's see here. Come on. Well, we need some point in the plane. We'll just take the origin because I like to always start at the origin. So our plane, you can use this form with the two directional vectors, 1, 2, 3, times the variable s plus 2, 1, 2 times the variable t, right? And this is a form of, or an equation for that plane. We can also take the cross product of the two vectors, u cross v. Let's see if I can do this all in my head. What is this going to be? 1, 4, and negative 3 is the cross product. So we can use that, and we get that the equation, come on, pen. Come on, pen. There we go. The equation of the plane is x plus 4y minus 3z equals 0. Okay, so the span of these two vectors is a plane, specifically this plane, so long as we're assuming the origin is inside of that plane, if we wanted to talk about it in terms of the space it takes up. All right, so that's span. Spanning set, okay? Spanning, come on, pen. This would be a lot easier if it just worked all the time. Oh, there we go. Spanning set. The spanning set is, I'm going to start with some space. So let's say I'm starting with R3. and I'm going to ask, is this set of vectors, so, vector A, vector B, vector C, a spanning set? Oh, my handwriting is awful. For, you can see why I type everything, R3. Okay, so a spanning set, it's generally going to be a question like this. I'm going to give you some vectors, and I'm going to ask, is this a spanning set for some vector space? And essentially what I'm asking is the span of ABC equal to R3? Okay, so I want you to figure out the span of these three vectors. And if that span is a three-dimensional space, then then it will be all of R3. So remember, how do we do this? We want to find the rank of the row-reduced form of the matrix containing all three of these vectors as rows. So row 1 is vector A, row 2 is vector B, row 3 is vector C. Row reduce this, figure out the rank. If the rank is equal to 3, then we span all of R3. And therefore, ABC is a spanning set for R3. Excuse me. All right, so I don't know much else to say. I think we're just going to stick with that for now. So I hope that helped in terms of understanding what a spanning set is. If not, feel free to come and see me, and we'll work out more examples and talk more about this and what it is. So yeah, hope that helped. I'll next discussion coming up soon when I figure out how to stop recording this dumb thing. There it is.